Alright, hell yeah. So we have a new textbook. This is H.C. Verma. And we're going to do something cool today, because we're going to go over center of mass. And hell yeah. And we're going to go over center of mass from the idea of things are point particles. And then, you know what I mean, I think when you're in school, you just go right to, like, this is explained maybe once to you or not at all. And then you just go right to, like, hey, these two chunks of mass, you know what I mean, their center of mass is somewhere. And then so this is what we do. You know what I mean, we say, hey, what's the center of mass between these two, you know, things? And so we take the center of mass of that one and the center of mass of that one, and then we do our thing, and we find the center. But, and hell yeah. And then even in this technical way to explain it, I don't know, I'm kind of disappointed, because we have these summations of all the particles and their weighted average. We'll talk about that. But then for this M1 and M2 downstairs, you know what I mean, I would appreciate, you know, this is where I can come in on textbooks. You know what I mean, there's only so much room, and it's just kind of fascinating, even in this book, you know what I mean, how they explain concepts, because they're going to use the littlest room possible, you know what I mean, to explain something, and then go on to problem sets. So hell yeah. So I do dig it. So yeah. So what is going to be below here? This M for M1 and M2 is going to be just the summation of the individual masses. So hell yeah. And so booyah. So that's what we're going to do. We're going to drive that today. Now the first one is just two particles in a line. So if I have two particles, and what they say is that they're going to do is they're going to take the origin right here. So let's go over this one and then try to tackle the more difficult one. So I want to find the center of mass between these two. Let's see if I can just do it kind of from memory. Is that I'm going to, so the equation for the center of mass, let's say, in the x direction. So we have, and we're just going to do that, capital X. So capital X is, so the summation sign is be like, hey, I have two particles here. You know what I mean? So we got I is equal to 1 to 2. You know what I mean? And if this is a summation sign, I was thinking is just like, what are the different ways you could write this? I mean, you could either, you could write this summation sign as I have two particles. I think this is the most important, you know what I mean, part of the summation sign. Hey, I have two particles. I have n particles. Okay. I'm actually, but we're going to get into it where, you know, maybe we're going to do two operations where I'm only going to use the second particle. You know what I mean? So I'm going to have 2 to 2. So now this is why you would do, I don't even think that gets explained very well. Because if I have, oh, and that makes so much sense. If I have I to n, and I have n particles, you know what I mean? So if I have, and they're going to do this like capital N particles, and let's say we have 100. So we actually have 100 particles. The summation of I to n, and then we're gonna, and then I think the first thing to do on this is like, hey, let's at least label our first particle, and then our second particle. And I would do, even in the summation process, you see this done a lot, and then you just go right on to like the dot, dot, dot. But what I would do is, I would go like 3 extra, you know what I mean? 1, 2, 3, let's go 4, and then 5, and get to a point where you're just like, nah, I really don't want to write all these, so then what can I do next? Maybe I can just do dot, 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 100. Okay, hell yeah. But there's one better that we can do, and that's put the ith particle, because in a lot of the MIT courses, you know what I mean, you're always going to be using ith particles, and you know, if that's in the x direction for the ith particle, maybe in the y direction, maybe you're labeling these as the jth, or maybe yeah, I mean, I guess I'm just thinking about vector or linear algebra. You have I and j. Maybe that's two-dimensional space that you're trying to say. But anyway, I am. Let's move on from that. So hell yeah. So I have the first particle, the second particle, the third particle, and still, my recommendation is anytime when doing these summations, just keep going until you're just like, oh, this sucks. And then, because then it's just like, oh, wouldn't there be a better way? So we're going to go sixth particle. Okay, now I'm going to go dot, dot, dot. Okay, and what if I wanted to do like the 33rd particle, and I'm just going to call that the ith particle? You know what I mean? So this is the ith particle, and then I'm going to go dot, dot, dot. Maybe I do like I plus 1. Okay, hell yeah. Oh, I could have done, you know, I minus 1. And then even with that, if I get to the ith particle, you know what I mean? I think when you're learning these summations, do it to the point where you're just like, no thanks. You know what I mean? And so we're going to do I plus 1, I plus 2, I plus 3, I plus 4, and then go the other direction. I minus 1, I minus 2, I minus 3, I minus 4. And then you're just like, okay, I get it. Okay, now we're going to go to the nth particle. And so we're going to go to that nth particle, and that's going to be 100. But then I could also say if that's the nth particle, this would be n minus 1, n minus 2. And again, do this until you're just like n minus 3. Do it a bunch of times until you're just like, okay, I get it. You know what I mean? Because if you don't do that, then it's going to get real techy, where you just have, you could do this, particle 1. I mean, typically they're going to do this, particle 1, particle 2, particle I, particle n. You know. And then you could just do particle 1, dot, 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 particle I, particle n. Alright, hell yeah. And so this is going to be related to our, so right here, you know what I mean? And it's difficult. When the textbook does something, I just feel like I'm not going to be able to follow it or something. Sometimes that's the hardest part, is just to figure out what they're doing. So, yeah, and that's what they're going to do. They're going to say, hey, this is a collection of particles. You know what I mean? And this is a collection of particles. So let's say this is particles 1 through 50. And this is particles 51 through 100. This is another strategy that you can use, is just to actually throw numbers at it. And so, you know, and in our little proof here, we're going to be, you know, summing particles 1 through 50. And then we're going to be, you know, and then summing, you know, particles 51 through 100. And so, hell yeah. So if I do say, oh yeah, hell yeah. And then what they're going to say is that the summation of each of the masses of the individual particles, because then they're going to do this. They're going to say, hey, the individual particles have mass. And so all of these are mi. You know what I mean? And this could be M1, M2, Mi, M49, and then M50. Hell yeah. And so then we have it. We have our M1, M2, Mi, Mn minus 1, and then Mn. Okay, hell yeah. But in this they're going to say there's going to be N1 is going to be 50 particles here. And then they're going to say N2. In this chunk, there's also 50 particles. So we have our two systems. We have 1, and then we have 2. Alright, hell yeah. I think we can almost explain this I and J thing on linear algebra. Because linear algebra, I just started studying it and finished the book, I guess. It deals with things that are perpendicular to each other. So vectors are perpendicular to each other. So if I have, and vectors are like, hey, if I have something that's, this length, and I move it to this length, and I just move it along this path, like this height didn't change. So here's your vector. And if I have a vector like that, and I just say, hey, I'm just going to move this vector, it's going to be more in this direction, the x direction. It doesn't change in the y. So therefore, if you have, some things, or vectors, when they're perpendicular, they don't interfere. So I can do anything in this direction, and it's not going to have any change into the magnitudes of those vectors in this direction. So that's why we can, associate, maybe this direction to be the I direction. Alright, hell yeah. And this direction to be the J direction. Now, they don't do that in this book because they just say, hey, we're going to have some sort of distance in the x, and that's going to be related to that particle. So we're going to say, if we have mi, mx, it's, hey, this m1 particle, and then it's from like maybe the origin, its distance, but the distance is in the x direction. And so we're going to call that the xi direction. But then we're going to come up here and then have this as the y direction, and it's going to have a yi. And so, I don't know how to explain it for this video, but it seems like you don't even need to have this y term. You could just have your particles as I and j, j terms. So you can have, like in linear algebra, and it's kind of just fascinating because in linear algebra you'll have something like this. You'll have like vector x, but vector x can represent the x, y, and z directions. So that's kind of what I was trying to get in this little side, but we should probably get on with it. So you might have like, hey, vector x, just any sort of distance vector could be in the Cartesian or three-dimensional space could be represented as ijk. But yeah, so that's the difference between, they're going to keep all the I terms the same, because when it comes to the distance, this is going to designate, what distance we're talking about. This is going to be, in the x direction, the distance of the ith term in the x direction is this perpendicular distance. And then in the y direction is going to be that perpendicular distance. Alright, hell yeah. Alright, hell yeah. And then I'm going to use my own medicine. So if we actually sum the masses of this particle, I'm going to sum mass 1 plus mass 2. And again, I'm going to use my own medicine. I'm going to do this until my head explodes. M4 plus M5 is like, okay, I get it. Plus ... M50. And here I didn't use any i's, but I could have done ... mi plus ... M50. But then, what are my I terms? Because these are each of these is mi. This is mi. This is mi. So yeah, so that's the other thing that I forget is the ith term isn't just one term. These are all the individual particles. These all can be considered mi particles. And so we have mi particles, and the I terms can either be 1, 2, and again, you know what I mean? So do this until your head explodes. 3, 4, 5, okay, I get it, and 49, 50. Okay, so my I particles can go from 1 to 50, and even just, I don't know, write your own mathematical statements. But hell yeah, so when we actually do this summation sign, they're going to say I for this is going to go from 1 to 50. And then we can see from that this is going to go from the I particle of particle 51 to particle 100. So, well, damn it. Alright, no, I'm glad, because actually we can have a J value here. This would be the perfect opportunity, because we have mathematical ways of explaining things. If I'm going to say that this is 50 particles and this is 50 particles, and this is also M1. Alright, hell yeah. So, camera cut out, but nah, this is cool because I don't back down. And I think this is cool because I don't get afraid. And so I think that's kind of what makes my videos maybe juicier, is because now we can just use our own mathematical constructs. And sure, if I'm going to call these particles also 1 through 50, so this is M50, I'm going to say this is the mjth particle. You know what I mean? So I'm going to have j particles. So I'm going to have J1, so M1, and I'm going to have particle M2, M3, MJ, and M49, M50. And so, hell yeah, I'm going to have J particles 1 through 50, 2, 3, 4, I get it, 49, 50. And so, and that's very similar to what they do here. Because, you know what I mean? And you could label these particles also 51 through 100. And that's probably also what they're doing. So if you're going to call each of these just I terms, where you have I is equal to 1, then that's what they did. They labeled these terms, 51 through 100. And you could have even mixed. You could just say, hey, this is particle 1, this is particle 2, this is particle 3, this is particle 4. But what they're designating here is that like so for this first one, well, let's see. No, this is cool. No, because we can actually read this. It says that the first particle, the I is equal to 1, is in this group. And then these particles are going to be numbered up to N1. So this N1 is just a number. And then for this particle, we're going to start at N1 plus 1. So yes, if this is 100 particles total, this is 50 and this is 50, then these particles are labeled 1 through 50, and these particles are labeled 51 through 100. But again, let's see if we could do it the same way. If all we're doing, and then they're taking the mass and multiplying it by its distance and then summing it. But let's just say they're summing the mass. So the way that they did it, so let's at least do it the way that they did it. So we have, and what we want is basically we want the total mass 1 plus the total mass 2. And so we're going to sum all the individual masses. So we're going to have a summation of, and this is going to be mass 1 through 50. So I is equal to 1. And then for this one, our N1 is going to be, there's 50 particles there. But this N2, it's not that there's 100 particles here, but just the way we're numbering them. And I should say it this way. This system has 1 to N1 particles, or 1 to 50 particles, where this system has 51 to 100. Those are the particles. And that's going to be N1 plus 1 to N2 number of particles, where N2 is 100. So that's what we have right here. N2 is 100. Hell yeah. And so we have I is equal to the first particle up to, or for this mass, for this first mass, we're going to sum the individual particles from the first particle. That's the ith, like all the I particles are going to be 1 to 50, N1. Hell yeah, and those are going to be the particles. I should have even wrote that first. Plus the summation of each of these particles in this second system is going to be the 51th particle. So if this is 50, we're going to be N1 plus 1 to the 100th particle, or just N2. So that's the summation. And let's see. Oh, and then even bugger. Okay, they're still just going to say M2 is 50 part. We're going to say, hey, the total number of particles in this system. So yeah, so we're going to use this capital N as the total number of particles in a body. And that's the cool thing about just reading a textbook, is like, what are they doing? You know what I mean? And then I'm just going to try to copy that. So the total number of particles in this body is going to be N1. The total number of particles in this body is N2. This is 50, and this number is also 50. When I go to label these particles, though, I'm going to label these particles, and let's see what they did. They labeled these particles 1 through 50, and they labeled these particles 51 through the summation of both of those, 51 through 100. Hell yeah. Okay, so we have mass 1 plus mass 2. Mass 1 is the summation of the I particles from I is equal to 1 to, let's say, I is equal to 50. Do with numbers first, especially if you're struggling like I am. And then I'm going to go I is equal to the 51th particle to I is equal to the 100th particle. And now I'm going to see how to put the letters in. So I have, and let's get better at the summation signs. Holy. Alright, so we have the mi particles. You know, of this first body, we're going to have a bunch of particles. We're going to sum them to get the total mass. And then I can even say it a little bit better. In the second body, we have individual particles. When I sum all of those, and I know each particle has a mass. That's what I wanted to say. Each particle has a mass, and then when we sum each of those particles, we get the total mass. So at least that makes complete sense. Hell yeah. So we have I is equal to 1, and now we can get techie, and this is going to be 1 to n1. And then this particle is going to be I is equal to the n1 plus 1 particle. We're going to add that one to the next one, to the next one, all the way up to n2. And this is where I need to, you know, it's really good to watch the higher up math videos and physics videos, because sometimes they don't skip. You know, they took, it almost took like graduate school to actually be like, nah, like I'm using this all the time. I really need to say this is also the ith particle. Like, the ith particle is not 1, and we just said, it's just like, if I have particle, this is, you know, this is particle 1, this is particle 2, this is particle I. This is particle n minus 1, this is particle n. Well, hey, can't I say that this is particle I, this is particle I plus 1? You know what I mean? So I can put that I anywhere, so let's practice that. And let's put the I right here. So this is particle I, this is going to be I minus 1. This is going to be I minus 2. This is going to be I... well, if this is n particles, and this is 1, and this is, no, this would represent, like, let's say this represents 50. This is going to be 49, 48, so then this would have to be the first particle. So I could also do this. It's just like, I want the number 1 is equal to, and then just use addition. So we're going to do 50 plus what is equal to 1? Well, negative 49. So this is I minus 49, and this particle is I minus 48. So hell yeah, I'm glad I did that, because the ith particle can be any particle from 1 through your system. You know what I mean? Alright, hell yeah. So this isn't even the route that I really wanted to go down, but I'm glad I did, because it really helps when we do this. So, and you know what I mean, maybe this video we don't even really understand what the center of mass is, because I do want to make other videos on that. I think the center of mass, the most logical thing for the center of mass is to always, the easiest way to envision it is, like, it looks like this one's bigger and this one's smaller. You know what I mean? If this was a thin piece of wire, like rigid wire, and these were two steel marbles on the end, you know what I mean, and you had to balance this, and it's quite long, and then so where would you be able to put your finger and balance it? Because I think humans, we kind of have that kind of ingrained in us to be like, hey, if I'm going to pick this up balanced, I'm going to maybe pick it up right there. And so that we're pretty decent at. Okay, hell yeah. So let's just go over the equation for center of mass. So the center of mass in the x direction is going to be the summation. Let's just use a simple summation sign of each of the particles but multiplied by their distance. So what we're doing is we're actually giving their distance some sort of value. And this is where using, and maybe we will get to it, but so you have some sort of mass, but then we're going to multiply it by a distance, and that's going to effectively, give that value more significance. But then we're going to divide it by the summation of the masses. And so this part is called a weighted, the whole thing is a weighted average. Because if you are saying there's something more significant about this one, or maybe there's something more significant about this one and less significant about this one, then instead of just being like numbers on a line, this could be 0 and this could be 1. Well, the average between them is just 1. And the reason is because each number, and maybe I should have said this is 1 and this is 2, but let's say 0 is an integer number, is that each number is given, a singular value. Each number is just only one, an equal distance separating the numbers, and that doesn't change. And so, so they have a weighted average of 1. Each number is only associated with this value of 1. And so if we do that process, so let's actually change these. Let's do the process of saying this is 1 and this is 2. My center should be 1.5. And this is an equation that, this is one where I kind of joke of like equations that I graduated without knowing. I kind of forgot them or just never learned them. Is finding the average between two numbers. And it's the weighted average, you know what I mean? But if it, simply put, it's just, hey, 1 plus 2, like add the numbers and then divide by 2, and you'll get there every time. And so that's one that I'm just going to mentally know that that's the average between two numbers. Add them, divide them by 2. But even if we slow down on that, we can look at what we're doing. We're going to sum, so we're going to say each, so how do you relate it to the sum of the masses and the distances divided by the sum of the masses for the average between two numbers? So I'm going to say the number is mi. So I'm going to say the actual number, and we're just going to say this is the number and the value of it. So and in our system, I have this is I is equal to 1, so I have one number there. This is I is equal to 2. So my total system, I have n, my total system is 2 particles. So or 2 numbers. So that's what we're doing on this one. So we have 2 numbers. This is going to be the value of that number. And now I'm going to take that value of that number and see this, I did it wrong. You know what I mean? And that's all right. Is this part would represent the fact that each number is only, like each integer number is only one of these. You know what I mean? So this is going to be the mass of the number. So each integer number can only cover a distance of 1. We could consider that number or that area to be a mass. And then so that mass is 1. Now, xi is the distance to that mass. So the distance xi to this first number, and so let's get rid of this because our origin now is going to be over here. And then so the distance to this first number is going to be 1, and the distance to the second number is going to be 2. And so this equation will look like this, and then we have to add the total masses of the numbers together. So here we go. We're going to take the mass of this first number. We said each integer number has a mass of 1. It has a distance from the origin of 1. And then we're going to add it to the next. We're going to do the same thing to the next particle or the next number. And that's over here. So we're doing this. The distance, the average distance between 1 and 2. So I'm going to say this is an integer number. It has a mass of 1. The value, any integer number just only covers that space of 1. And cool. And then its distance is going to be 2. And then I'm going to divide by the total masses of the numbers. Each of these numbers are just, has a mass of 1 each. And so the mass of the first one is 1, plus the mass of the second one is 1. Sorry for putting parentheses there, but just, I don't know, since I was like encompassing these as masses, hell yeah. Alright, so we have, so this is 2 plus, this is 1 plus 2 divided by 2. So there you go. So that is the relationship. It's going to be 1 plus 2 divided by 2. It's whatever number that you have, and might as well do that one again. So we're going to go 1, 2, 3, 4, 5, 6, 7. And we're going to, like, hey, let's say the average would be right there. So I'm going to take this number and this number. And then this is the origin. And we have 1... So we have distance of 1, 2, 3, 4, 5, 6, 7. And cool, and this is particle 1. So this is mi. This is going to be m1. This is going to be m2. We can even write this is x1 and this is x2. Hell yeah. Alright, so we're going to use our equation that the center between these numbers is the summation of mi(xi) divided by mi. So you're summing, and then let's even put these in. So we have I is equal to 1 to 2, and then I is equal to 1 to 2. We have 2 particles. Okay, the mass of this number is just 1. And then I have a distance of 3. And then I'm going to add it to the mass of this particle is 1, and it's a distance of 7. And then we're going to add the masses of the particles together. And we're just saying one integer number covers an area of 1. That area might be associated with a density, or a volume, and and a density. And so hell yeah, that mass of that number is 1. So sweet, we have 2 of them. So the mass of this one is 1, and the mass of that one is 1. Hell yeah. So I'm going to have 3 plus 7, it's going to be 10, and then this is divided by 2. So the average would be 5, and that's what we would get. We would get the average right there. Alright, hell yeah. Alright, booyah. But now for our problems, we know that if these masses are different sizes, like just visually this one's bigger, it's center, like if I have to pick this system up, and have it be balanced, I'm going to be pulling it from over there. So let's do it. So we're gonna set, this is our origin. This is mass 1. This is mass 2. This distance is d, and they're going to say this center is going to be c. And so I could say the center of mass in the x direction, which if I take it from the origin is going to be this value of c. So I can say c is equal to the summation of the masses. So I take the mass and then the distance to that particle, from some point. And this is cool because I can choose whatever point I want. I could choose the midpoint. And so maybe we'll try to bust this out 3 different ways. Okay, hell yeah. And then we're gonna and then this is the definition. So it's the weighted average. So I'm going to take a mass and then find its distance from some sort of point. And then I'm going to divide it by the total mass of the system. Cool. And for our system, we have I is equal to 1 to I is equal to 2. And I think, hell yeah, even just writing I twice here is a good way to go. Cool. Okay, so we have this mass is going to be m1. So let's get our equation. So this first mass is just going to be the mass of that particle m1. The distance is going to be 0. And then, and don't, know that that's the first mistake you can make is this division sign. You have to do everything in this step first. So sometimes maybe it's useful to put this bracket right there. And then you got to do everything first. So, put your bracket in, do this. Maybe that's a good way to start. Put this bracket in. Do that before you start dividing. Cool. The second particle is going to be the mass of the second particle. Its distance is going to be d. So we have that. And then we're done summing and this is called the weighted average. So we're taking the mass and multiplying it by a distance. And that's where, for future videos, I'm going to be talking about how this is the first moment of mass. So you have the definition of a moment of force is just, force times distance. It might be the dot product, but it's just force times distance. And the first moment part is the distance. Because if I have mass moment of inertia is going to be the mass. How am I going to... I'm going to have the mass, and then it's going to be the distance squared. It might be mr squared or something. But here's the mass and the distance squared. This is going to be the second moment. So I'm taking some sort of quantity and then multiplying it by a distance. And I don't know if you could call something a moment or a second moment if this other property wasn't a distance. You know what I mean? But I think, I'm going to look that up on Google, but I think for all moments, don't quote me on this though, that's a good thing to look up on Google, but for any moment, whether it's the first moment of this, the second moment of that, is some sort of physical property that when you multiply it by a distance, now we've got something, that's useful, mathematically useful, or just useful in a physics perspective. But I think the word that comes up here is leverage, whether you're talking about a first moment or a second moment, you're taking some sort of physical construct of the universe or mathematical construct of mathematics, and you're multiplying it by a number. And so that's significant because, we're talking about individual particles this might be different for different things. This particle might be multiplied by something small or no distance, and this bigger particle is multiplied by a bigger distance. Well, now you see that, Well, that's going to be kind of now on steroids. You have a physical property multiplied by another physical property, and if both of these are, doubling, then cool, you get a times 4 compared to that property. So moments are going to be leverage, and that's why you can have this mass is twice this mass, but when we go to pick it up, yeah, hell yeah. Sometimes I have to take a pause, but yes, if this mass is twice this mass, when I go to pick it up, my center point means that this distance will be half that distance, because leverage is a physical property times a distance. And so if this has twice that physical property, then this distance is going to be half. If this has half the physical property of that, this distance is going to be double. So I think and I'll try to make snappier videos or just more in-depth on that first moment of mass. But hell yeah. So that's why I said, envisioning this as picking it up and balancing, because what you're using is one of the Newton laws of the fact that when something gets torqued, it wants to cause rotation, and to balance that torque, you have to and torque is a moment. It's a force, so torque is force times a distance. So if this is generating a torque of a value of 2 times a distance of 1, and this is only a value, a physical property of 1, this distance has to be 2, because the multiplication of these two have to balance. So when you pick up something, the torque caused by this is going to be the same caused by that. And so that's literally, even when we have this system, think of all the particles actually attached, and then so this is where the the thing that you can do in physics is to, make everything attached by just a foam board. You know what I mean? So I just have a chunk of foam, and I'm going to call it a massless board, but then I have these really heavy steel, marbles, or like, steel cannonballs on this foam board, and just make sure your foam board visually for you is strong enough to hold the system. But then hell yeah, now all the, and then and even if it's just a physical property that's going to be in this state for a time, at this moment, at time 0, that's where it's going to be. Then still you could pretend like it's rigidly, at least in that moment, even if it's a dynamics problem, in that moment, this is where the particles are. I'm going to attach them all together by like a foam, board, and then I can figure out where I'm going to balance that. And again, you have to put an earth underneath you and then have force, but I think that's very useful because that really shows what the biggest property, that I can think of the center of mass is the fact that all these masses want to be attracted to the earth. And even though the earth is round and it's centered and it's going to be a distance to these, the earth is so large that all the force field is just directly down. And then so to balance these, you're going to have a balance point somewhere. And again, it's because these masses want to cause a rotation that way due to a torque, and these want to cause a rotation that way due to a torque. And from that center point, the torque caused by that little chunk of mass is going to be the distance to that mass times its force, and that's going to be F equals ma. And so A in this is going to be your gravitational constant. Let's say it's 10, but that's a constant. And then so you literally have the torque is the distance, xi times mi, plus that g term. And so there you go. So it's you're literally doing one of the easiest things to see. But I had to look this one up because it's still a mathematical property. This is still a weighted average. Or just center of mass is a property unto itself. You don't have to have the fact that if you throw G here, you get a torque about the center of mass if you put this on the surface and balance it at that location. Alright, hell yeah. So to finish this problem, and then we have the total, we're going to sum each of the masses together, so we have M1 plus M2. And then so this relationship, we're left with that center is going to be M2D divided by M1 plus M2. Hell yeah. So that's what we have. And then that's going to be probably for another video because I'm about done and I want to get to this. I want to show that we can put summation signs for that. That's all I wanted to do. You know what I mean? And then just see how you go from, taking any arbitrary, and then I said I was going to do this one 3 ways, so let's do that. So let's set, or just at least one other way. Let's set our origin right here, and we know that this is distance. This is going to be d divided by 2, and this is d divided by 2. So if we do this, hey, this is the positive direction, this is the negative direction, if we're calling this the x direction. So now, and then you could see that if the masses were of equal size, the center would be 0, but now we're going to be some sort of offset. Yeah, so let's get a fresh sheet of paper, and let's just use the term x. So the distance x from the origin is going to be the center of mass of this system. So we have the summation I particles I1 to 2, the mass of the particle times its distance from the fixed reference point divided by I is equal to 1 to 2 of the mass of the particles. And so from here we have this first particle has a mass m1. Its distance is going to be negative d divided by 2, so we're going in that direction, plus the second particle is m2, its distance is d divided by 2, and then we're going to divide by the total mass. It's just going to be m1 plus m2. And so, hell yeah. So this is going to be the x direction, well, let's keep it fresh. All right, hell yeah. So our center is going to be, so let's see what this is. This is, yeah, what should we do here? Let's, I hate negative, see, 'cause the negative gets me down. So one thing that you can do is take your time, and then take that negative and just make it a -1. And then it's d divided by 2 plus, and then so there's that m2d divided by 2. And then I can see that I can factor out that d divided by 2. So let's start this one over. So I'm going to do d divided by 2, and then I'm going to have m1, -1. Yeah, this is my favorite way just to, like, you know, capture the negatives in a bubble, and then they don't ruin my day. Hell yeah. And so there you go. And then we're going to divide it by m1 plus m2. Alright. Hell yeah. And then so I guess this would be, the formula for this would be d upstairs m2 minus m1 divided by 2 times m1 plus m2. Okay, hell yeah. So yeah, and you're gonna get the same values. Alright, but let's double check this. How would we double check this? We said when the center, this C, was from this origin, it was going to be that total distance. We said if our origin is right here, this is the distance that we're getting. This is our equation for that distance. And so one thing that I can do is I can take this distance and then add it to d divided by 2. So that's what I'm going to do. I'm going to add this to d divided by 2. And then what I should get is this. You know what I mean? The center from this. I should get this formula. And I probably will. And let's do it. So the denominators have to be the same. So I have to multiply this by an m1, m2 downstairs and an m1 plus m2 downstairs. So that's all I did. Just multiply it by the same value upstairs and downstairs. And then so my denominator is now the same. Now I can add these. I'm going to say this is dm2 minus dm1. And this is going to be plus dm1 plus dm2. And then I can see that my dm1s cancel. And I'm going to have 2 times dm2. So I'm going to have 2 times dm2. And this is in the form of m2d. So let's switch that around. Sorry about that. So we're going to have m2d and 2 of those upstairs. I'm going to have, and the downstairs has a 2 in it. So let's just get rid of the 2. And I'm back to m2d is m1 plus m2. So hell yeah. And that's right there. So we're good to go on that. I'm sorry I did a little bit rushed, but I think just going through it is beneficial. I could have not gone through that, you know what I mean? So hell yeah. Alright, let's see if we're going to talk about this. Alright, hell yeah, home stretch. So we will use this picture to show that, hey, maybe this mass is going to be those particles, and then we have another system of particles over here. And so, so just know that this mass and this mass is just a system of particles. And it's got so many that they all blend together, so it's kind of like a solid. But it's just kind of nice to be like, hey, let's say there was just 50 in each. So that's kind of what we're going to do. And then for our equation of center, you know, we can choose any location. So let's say this is just that particle is the one that's the farthest that direction. And so maybe I'm just saying, hey, that's a good place to throw my axes. And so let's maybe call that particle 1. Cool. This has particles 1 through 50. This has particles 50 through 100. Cool. The total number of particles for this, for N2, is 50. And then the total number of particles right here is also 50. Okay. So, But this proof says if I do find this location, so if the center of this is right there, C1, and the center of this one is right there, and we can do this process for the y direction the same as the x direction. And because, like we said, they're perpendicular, they don't interfere, we can calculate the x direction one, and that's not going to interfere with our calculation for the y direction. And so just for the sake of time and my limit for this video, I'm just going to do the x direction. But what this says is that, hey, if I find this distance, x1 to there, and this is the distance x2 to the center of there, then, and what I can do is I can take that the center for the whole system, maybe center star, is going to be the summation of, well, it's just going to be m1. I mean, now I'm saying, like, hey, this is one particle and this is a part. So I'm basically reducing. But how would you say it? Because you're not. Yeah, you would say that it's going to be m1 x1. So the mass of this total system times that distance plus the mass here x2 divided by the total mass. And I just think the fact that you lose your summation signs and you're not, well, yeah, so that's what that is. And then that's what this equation is. So it's the, but you know what I mean? And they explain it this way in the textbook, but then this is like what they use to start that process. And I just thought I was bummed out that they didn't put a summation here of mi from I is equal to 1 to n1, and we can do this, you know what I mean, because it's kind of tricky to figure out what goes on the summation signs. This is mass 2, so we still have mi particles. They're going to start from 51, so that's n1 plus 1 to, yeah, and I'm just going to put an I up here. It helps me. And this is going to be n1 plus n2. Cool. Whoa, I'm glad I did this because, hey, isn't this is the kicker right here. I mean, well, all of them are, but like this M1, so M1, let's do the easy one first, is MI, the summation of MI. And if it's M1, it's going to be I is equal to 1 to I is equal to N1. We're getting faster at that. But this X1 term is going to be, you know what I mean, the full equation from, all these particles. That's going to be the summation of MIXI from I is equal to 1 to I is equal to N1 divided by the summation of the total mass of M1, which is I is equal to 1 to I is equal to N1. That's going to be that term. You know what I mean? This mass 2 term is going to be this. So, I mean, I guess I could say that's mass 1. Mass 2 term is going to be the summation of I is equal to N1 plus 1 to I is equal to N1 plus N2. And that's going to be the summation of those masses. But for sure, this X2 is also going to be this, you know what I mean? And I can write it again. You know what I mean? It's going to be the center of these particles, from the origin that we chose. And that's going to be I is equal to N1 plus 1 to I is equal to N1 plus N2. N1 plus 1, I is equal to N1 plus N2. I is equal to 51 to I is equal to 50. This is 51, my bad, to 100. If I said that right. 51 to 100. Cool. So now, no, I do have my work cut out for me. That was fascinating. So what they're going to, and this is kind of what I've been learning from proofs. I don't know. It's not maybe a technical way. But if they are saying this, like if this is the equation that we're trying to say, if I'm saying like, hey, I know the center of mass of this body, and I know the center of mass of that body, I want to know the center of masses between them. I don't want to do this integral of, well, it's not an integral, but a summation of all these masses, And yeah, for sure, this is the integral process. Like literally, it's the integral process. But you know what I mean? I don't want to do that. I just want to know, like, hey, this round circle has a center in the middle, and this square has a center in the middle, and then the center between them. So I think this might work out. So if this is what we're trying to achieve, this would look like this. M1 has to be this quantity right here, multiplied by this quantity right there. If I can get that, you know, right there, and then M2 is going to be this quantity multiplied by that quantity, and then this M total is going to be the summation of those two. So if I can rearrange my equation to get all of those right here, then yes, I can use this formula. So that's what I'm going to do for my proof. And so what we're going to do is just find the center from the origin of the system as individual particles. So we're not going to be caring about what order things come in. We can rearrange the order later and see if we come up with this. So that's going to be my strategy. So I'm going to be the center of mass of this system in the x direction is going to be, and then, yeah, the total mass is going to be the total mass of all these particles. And so I'm just going to say it's, yeah. So let's see if we can just do this. So we're going to be summing particles. They're going to have, I'm going to take particles 1 through 100, and then find their distance from the origin this way. And so they're going to have, each of these particles is going to have a particular distance. And I can just pick an ith particle. And then I can say, hey, this is the distance xi, and this ith particle is going to have a mass. It's going to have a mass. So it's going to be the ith particle, mi, and the mass is the value right there. Hell yeah. And then and I'm going to do that for all the particles, and then divide it by the summation of those masses. Cool. And this is going to be, 1 through 100. Alright, and then when I start to do that process, I can have M1, x1, plus M2, x2, plus dot, 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 and then I could have M50, x50, plus, and then M51, x51, and then dot, 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 all the way to M100, x100. And then what I can do is I can group these using the associative property. Even if they were all out of order, even if like particle 1 was right here and particle 2 was right here, that's definitely going to change my summation sign, but I can still group particles however I want. And so hell yeah, so I'm going to group these particles 51 through 100 multiplied by their distances, and that's going to be called the weighted average. No, that's going to be the weight. That's going to be the weighted term. Dividing by the mass is probably what you would consider the average. But yeah, it's still leveraging. I'm taking a mass, and then it's leveraged. It's being leveraged by distance. So this is first moment of mass. And so that's really good to see, is that we have a mass times a distance, and that's going to be a first moment of mass. Alright, and then for the downstairs terms, I'm going to have M1 plus M2 plus dot, dot, dot plus M50 plus M51 plus dot, dot, dot plus M100. So I can group those together. Alright, cool. Alright, hell yeah. So I think I don't know if I'm not making an error, but I think we almost need to just start dividing things because, for this to work, we have, like this term right here is the center of mass of those particles. So, you know what I mean? let's just do that term. So if I just have x1, the center right there, what is that? That's going to be the summation of m. So that's going to be m1x1 plus m2x2 plus m50x50 dot dot dot. And that's going to be divided by m1 plus m2 plus m50. So that is going to be that term. And that's what I need right there. Alright, this might be more of an experiment. I guess I didn't do this. I guess I didn't do this. I just thought I could do it real easy. And but at least if this is my divisor, and I can use this associative property, I can separate those two. So I can have m1 x1 to m50 x50 divided by m1 plus m50. So that's what I have right there. This side, is going to be m51 x51 plus m100 x100 divided by, see, and I messed up. This is still m100. It's still the total. I still have to divide by the entire denominator. And so this is going to be m1 plus, same thing, m100. Okay, hell yeah. So now I can just kind of focus on this. What I'm trying to get this to look like is, yeah, and I'm trying to say this is going to be the m1 x1 term divided by m1 plus m2. Alright, hell yeah. But this x1 term, that's the kicker, because that x1 term is going to be the summation. So it's going to be m1 x1 plus 2m50 x50 divided by m1 plus all the way up to m50. And so this I don't have right there. I mean, I just have that part. And then so, you know what I mean? This is sometimes in mathematics, you're just like, well, write an equation for what you don't have and what you want. I mean, that's kind of what we're doing with this whole proof anyway, is we're trying to get this upstairs. And if it was multiplied by m1, then that would be m1 plus m50. Let's smooth out those. All right. So, and then now we can see that this x1 term, so now what I just did was, this is now x1 times m1, and it's written in the order of x1, m1. So that's what this is. This is x1, and then this is m1. Hell yeah. And then so, therefore, these two cancel, and you're left with this. Alright, hell yeah. And I think it'd be more useful to go the other direction. You know what I mean? If we are saying, so we'll try one more time. But if we are saying that this is our equation, that the center of mass is the total mass times the center, plus this total mass times the center. And if I had more of these, like this is literally now M1 and M1 and M2, where I is equal to 1 to 2. You're doing that. And so I think working backwards would make more sense. So if this is the mass of this particle, then I would say that, and I think that's what I want to do anyway. So we have x is equal to, this is going to be the summation of mi xi from 1 to n1. Cool. This is going to be the summation of n1 plus 1 to n1 plus n2 mi xi. Hell yeah. And damn it, we're going to have to probably use a lot of paper anyway. So yeah, and sorry for writing so small. But yeah, let's do this. So this is well, I can just literally just rewrite this equation. So we have m1 x1 plus m2 x2 m1 plus m2. Alright, hell yeah, now let's do it. So this is going to be mi. So this term right here, all we're doing is just focusing on literally that term. This term is the summation of, and I'll just do 1 to n1, and just know that this is I, particles I. Hell yeah, so that's that term right there. Now this term, you know what I mean? X is going to be the summation of mixi divided by the summation of m. And I think this is useful to actually drop the i's because, I don't know. I guess this is just I is equal to 1. What do you do? I is equal to 1 to whatever. You could put a k right here, or just an n. Okay, hell yeah. Okay, but that's going to be our next term. And so we have the summation of 1 to n1 mixi divided by the summation of 1 to n1 mi. So that's that term. Now we're going to add the second mass is going to be n1 plus 1 to n1 plus n2 mixi. Ah, damn it, it's just mi. So we're just focused on that one right there. Now this x2 is going to be this equation. n1 plus 1 to n1 plus n2 of mixi divided by n1 plus 1 to n1 plus n2. 50 plus 50 is 100. So this is 51 to 100. Cool, so that's the x2 term. And then we're going to divide it by m1, which is particles 1 through 50, the mass of those, plus particles 51 to 50 plus 50 is 100. 51 to 100, and those are the mass of m2. Okay, hell yeah. So now we have so now we can rearrange this, and what we're hoping to achieve is we're hoping to achieve this, is that the center is just going to be all the particles, their weight, m1x1 all the way to m100x100, divided by the total mass. You know what I mean? So this is the total mass, so we're trying to get this top part to look like this. Is just, and so we're going to see what cancels. And then we can, so now it's just obvious, is that those cancel. Those two cancel, and those two cancel, and so you're just left with mixi from 1 to 50, and then mixi from 51 to 100, which is literally just mixi, 1 to 100. So that's what we have. We have the summation, which is the mass times its distance. That's the leverage. That's the weight. That's not the average part. That's just the weight part. That's the leverage. That's the first moment you have some sort of mass out at a distance. So like, booyah, that's a leveraging of, the distance is leveraging that mass. So that's why it's that multiplication process. Alright, but hell yeah. So, not super clean. But I mean, this was clean. It just took me a while to kind of get here. Yeah, hell yeah. And then, so yes, when we cancel those and those, we're just left with this top part and the bottom part. And hell yeah. And so, and that's what they show here. You know what I mean? The center of mass of the system, total mass downstairs, and then the top is just the weight of this one plus the weight of this one. Divided by the total mass. Alright, hell yeah. Alright, and probably in this chapter it actually shows maybe that, because this is still the individual particles. But if we've already found the center of this one, it has a mass, m1, and a distance to its center, c1. And this is m2, c2. And then so again, that c1 is going to be this. This is going to be the c1 term. And this is going to be the C2 term for the center to this one and this one. From a fixed reference frame. And then you're just taking the summation of you're still doing a weighted average. I have one particle here, so this is M1, C1. There you go. So I have this mass 1, and it's a distance c1. That's going to be the leverage of that mass. And then I'm going to add it to, we have m2, c2. That's this mass, and it's going to be that difference. That's the leveraging of that mass. And then I'm just going to divide it by m1 plus m2, the total mass of the system. So it's kind of interesting how you can start with a bunch of ith particles, but then you can group them. And I just thought it would be so fascinating, because if I have, let's say this is 4 particles and this is 4 particles, I can literally find the center of mass between those two, which is right there, and then those two, which is right there. And then and then basically say that these are new masses. So now the system is just those, and then the center is going to be right there and right there. So now I have, and then I can take the center of mass of these two. And it's so interesting. A lot of physics is like, whoa, I'm doing that from even just this this reference frame. The center, even if I take it from some XYZ coordinate system, the center between those two is still going to be that value right there. And the center between those two is still going to be that value right there. Then I can do that process again and be like, what's the center between these two? And that's going to be that mass. So this mass is going to be 4 of the little particles. And I can do that same thing here. The center between those two is just going to be 4 of those little particles. And then the center between these also is going to be right there. So hell yeah. So at any stage of the game, you can take any 2 particles and find the center between them, and then just say that, you can treat those 2 particles now as if it were a particle with twice the mass, if the particles are all the same mass, particle of twice the mass at that location. Yeah, so I think that's a good place to end, but I just thought that was the cool thing that I just realized. Is just these are, you could take these 2 particles and say these are just a little blob, and then, and have a center, and then compare it to 2 other particles. Hell yeah. Alright, so, I think I'm done. Thanks for joining me. Booyah.